Howdy, everyone.
Hello. How are you doing, guys?
Pretty good. Hopefully you do as well.
It's fine. Just a little bit crazy. How's everything else? Are you ready for last 1.5 week of classes?
Nope, not at all.
Not at all.
Nope.
I see.
But we're going to do it.
We somehow should do it. We have no choice. We just somehow all will need to put ourselves together. So I don't see too many people. We're still missing quite a lot of people today. So guys, any questions?
I was wondering how the final was going to work. I saw on Canvas, or I guess the portal for CISA, that it was going to be something like 4 hours long.
Somebody wrote me email. Yes, I think in my syllabus I put 4 hours, or maybe it was whatever it is. Exam is 2 hours unless you have extra time. Okay, so unless you have your university give you like 1.5 times of time or 2 times more time for exams, in this case you have more time, but otherwise you have it for 2 hours. Okay, and it will cover everything. So it will cover your everything from the beginning of the course, including the end of it. So we might have like, I don't know, 1 or 2 problems based on the end of what you're studying it, and something from the first exams and from second exam. Okay. So I hope does it make sense? Okay. We start to have a little bit more people around. And what else? On Wednesday, guys, we will have our discussion session, and so we'll, instead of colloquium, so where you will have an opportunity to discuss how you're dealing with COVID, how is it affecting you, what kind of strategies you have, and because we'll need to find out a way how we'll teach it next semester. And it's more like for you guys, we'll find the strategies, and maybe you'll suggest like, oh, you know what, that faculty did this one, it was really helpful. I'm not saying that all faculty will use it, but at least will give you output, and also you'll hear what other students suggest. Okay, so that's pretty much for you guys to make sure that we find a way how we can all live together for the spring semester. Okay, anything else? Any questions, any comments before we start official lecture? No? Okay. In this case, we are moving to our second to last lecture. We'll talk about black body radiation. Okay. So let me put this spot for everyone. Is it spotted out? Now do you see the piece of paper, guys?
Yes, you pinned it to the front.
Okay, perfect. Thank you. Because sometimes I remember when I did something, people didn't see it all the time. So I just want to make sure that I'm using the right button. And let me start recording. Okay, so we're starting our new lecture. We'll talk about black body radiation. Your last homework based on black body radiation. This is a big chapter. We will not be able to cover it all, but we'll try to cover as much as we can, okay? So whatever we cover, we'll cover it in one lecture. So, just a second, something. The connection is not as good with it. As always, you know, you will get used to it. Guys, do you have is it blurry for you?
A little bit, yes.
Okay, I don't know what's going on. Okay, now it's good. Okay, now it's back to normality. Okay, good. So I'm glad that everything worked out now. Okay, so we'll talk about photon. Okay, first section, photons. Today it will not be normal lecture for me. My office hours was group meetings was all set with all this small disasters. Just a second, guys. Sorry. Okay, let's start again. Photons. Okay, so what is photons? First, guys, is it fermion or bosons photons? Questions?
Boson?
Boson.
Bosons particles. Okay, very good. It's a bosons particle. Anything? Do you know what kind of boson particles are they counted as?
Gauge bosons?
Yes, you're right. So photon is the gauge boson. But also electromagnetic. So what does the photon means? It's the quantum of light and all other forms of electromagnetic radiation. So it's the quantum of light and all other forms of electromagnetic radiation. So what else we can say about photons? Photons are force carriers for electromagnetic forces. Carriers for electromagnetic forces. Okay. It's doesn't have a mass. Oh, my internet.
It froze.
Again, I know it's froze. I don't know what's going on today. My internet. Guys, I'm sorry. This one, let me see one more time. It's just disconnected. We had this issue before. At least it's not a review. And it's not like we have a one short lecture about black body radiation. It's one of my favorite ones because it's related to optics. So I was trying to give you the quick overview. It's supposed to be here. Okay. Huh. Okay. Okay. It's still not working, guys. I don't know what's going on today. Sorry, guys. What what's going on with my lecture today? Do you see it now? Is it pinned down again?
No, right now it's on your face.
Am I not hearing any action notes with you guys as well?
Oh, it's a little blurry, and well, we can hear you properly.
Okay. How about I'll tell you a joke while we're waiting for my in.
I'm okay with that. Oh, now you definitely froze.
It's about somebody comes to the bar, yeah? Okay. Infrared Fatun walked into a bar and said, is it hot here or is it just me? And I could see the internet back, so I will try to go back to the lecture.
I want to laugh, but it's kind of still blurry a little bit.
Is it blurry?
Well, like even your you kind of cut off sound wise too.
Oh, really? Okay.
Oh, it looks good. Miguel?
Okay. Good, good. Thank you. I hope it will be good. Actually, I don't know what's going on today with internet. It's a little bit hectic today with me the whole day with internet. So let's try our best, okay? So photons are the boson particles we discussed as gauge bosons. The force carry of electromagnetic forces. So enough point about this. They are massless, yeah. Okay. What else do you know about photons, guys? With which speed they travel?
The speed of light
Yes, they travel with the speed of light
in a vacuum.
in a vacuum, yeah. The speed of light, which is 3 times 10 to the power 8 meters per second in a vacuum. Okay. Okay, vacuum. Okay, what else? It has two polarization states. Has two polarization states. Okay, in vacuum. Okay. It has a spin one. And related to what we are studying, it's a base, the Bose-Einstein distribution. Okay. And the Bose-Einstein distribution tells us that average number of particles is equal to 1 over E in the power of energy minus chemical potential divided by KT minus 1, yeah? Okay. Could you see this? Was it good? You can see the screen. So what else about photons? Something special about photons. Photons can be created and destroyed in any quantities. Photon can be created and destroyed in any quantities. Okay. The number is not conserved. And that's very special about them. Okay, because we used to have talking about situation when something is conserved. Again, it's blurry. So photon can be created and destroyed in any quantities. The number is not conserved. Okay, so how the photons could be created? They could be created, for example, moving the particles. If a charged particle moves, in this case, it will emit photons. And what kind of radiation? Do you know how this type of radiation is called? When charge is moving and it's emit photons. Did you ever have that? Concentration. Okay. Examples how it could be create examples how photon can be created. Okay, example how photon can be created is moving charge. So in this case, it will be example of synchrotron radiation. Okay. One, for example, during molecular, atomic, or nuclear transition to lower energy state, or during transition to lower energy level. Okay. During transition to lower energy level, and this could be molecular, atomic, or nuclear. Okay. Molecular, atomic, nuclear. Okay. So could you see it, or you completely couldn't see my? Oh, yeah, I completely lost you already today.
It's just hard because even the audio now sort of is sounding very choppy and not great.
Oh, really? Okay, let's hope that it will go better. Okay, I will put the notes. We have these difficulties today. What's going on with internet? Okay, so let's me in this case repeat some of the materials multiple times. So photons are most important. They are boson in two polarization states. That's very important. We'll use this later. And there be the Bose-Einstein distribution. And a special thing about photons, the number is not conserved, which is extremely important, so we can create and destroy them in any quantities. And let's look what happened. As we just discussed it, electrons could create photons. So do you know which letter we use for? We use it as gamma. Okay, gamma is a symbol for photon. So if we have an electron, for example, our electron could go through the reaction. It could go in one direction, in another direction, and it could create another electron at a lower energy level, and also create a photon. Okay. And that situation is in equilibrium, so it could go in one direction and another direction. So it's in equilibrium. And if we could write it in terms of the particles, so we get it particle as electron, and then we get particle and photon. We can write them in terms of chemical potential. We can write it as mu E is equal to mu E plus mu of photon, mu gamma. And all this is true. What should be mu gamma?
Should it be 0?
Exactly. So mu is equal to 0 for photon. And that's fundamentally important because photons can be created and destroyed at any quantities. And you can see that if we add them out, and the chemical potential should be observed, yeah, or before and after reaction equilibrium. So in this case, chemical potential for photons should be equal to 0. Okay, so in this case, photons obey Planck distribution. Photons obey Planck distribution. And we'll discuss this in a bit. So, and the Planck distribution is we're taking Bose-Einstein distribution, which is that one here, and we know that mu is equal to 0, so we can write the Planck distribution. It's a Bose-Einstein when mu is equal to 0, so it's E in the power of energy over kT minus 1. That's the Planck distribution. Okay. So now let's talk number 2. Let's talk about the Planck distribution a little bit more. So we can use similarly for photons as for harmonic oscillators. Similarly, harmonic oscillators, similar harmonic oscillators, we can write it down. Energy of each photons could be 0, then HF, for example, if you have particular frequency of photon, yeah, 2F, so on. Okay, so that's for photons. In this case, we can write our partition function Z as a combination of any possible states. Have a in E in the power of 0 energy, give us 1, then E in the power of minus beta HF plus E in the power of minus 2 beta HF plus so on. And that summation is geometric series, and it's equal to 1 over 1 minus E minus beta HF. So it's exactly similar to what we did before for Bose-Einstein, but here with a simple. So for n Planck, we can write it down that it's equal 1 over E in the power of HF over KT minus 1. Okay. And we just find out what is Z. Now, if we want average energy, we use our famous formulas. It's minus 1 over partition function, and then partial derivative of partition function with respect to beta. Okay. And we can derive with respect to beta. This will give us what? I mean, do you want me to do it, or you'll do it yourself, guys? Do you want me to write answers? I will just write the answers. You just, that's which we did similar before. That will just equal to HF over E in the power of HF over K minus 1. Okay, so that's average energy for photon. Now, let's talk a little bit more about photon energies. Let me put this as section number 3. In this lecture, I try to sum up only the most important parts of the chapter. The chapter is huge, so I just try to give you the most important things, and I just give you extra background about photons. So photons energy. So to find photon energy, we'll use the same formula and methods which we used before. So for quantum mechanics, we talk about particle in a box. So a box allowed wavelengths for photons photons. Again, my internet is dropped, guys. Could you see me again, or it's again dropping off, guys?
No, you're good so far.
So far, so good, good. Okay. In the allowed for photon energy in a box, allowed wavelength for photons will be lambda n, which is equal to L for photon is equal HF. Yeah, that's just definition. What is the energy for photon? And we can instead of using F, which is what does F, guys, stands for? Photons. Frequency. Okay, that's frequency. Okay. Frequency, and lambda is a wavelength. Okay, so we can write frequency in terms of wavelengths, speed of light over wavelengths. So this is another way how we can write a frequency. And we can plug in lambda here, and we can find out that energy in this case could be written as HCN over 2L. And I don't know if you did something similar in your homework, yeah, where you use a particle in the box and you find the energies. So 3D box. For 3D box, we can do exactly the same steps, and our energy in this case will be HS over 2L, and here we have a summation over nx squared plus ny squared plus nc squared. Okay. And we can find what is the average energy. Average energy for the box, yeah, box. In this case, U is equal to, we need to sum up over all these energies, that's U, and we can do it like that, or we can do it differently. We can use a formula where we sum over nx and y and z energy times, sorry, I'm completely lost you, I'm sorry. So we want to find the average energy. So to find the average energy, we need to sum up over all energy times number of particles for this particular energy. So it implies that energy times Planck distribution function, NPL, which we find before. I know I somehow don't do very good explanations here, guys. So remember we find this Planck distribution before here. As for photons, it's similar what we did with Einstein's distributions. So here's the idea. So to find the average energy, when you multiply energy, here we multiply by Planck's constant. Okay, I could feel like I completely lost you guys. Do I have anyone who's following me? I think not.
A little bit.
Okay, I honestly try to, the problem is I try to cut out the chapter to just give you the most important bits, as everything in these last sections. So there's one lecture per each topic. So if you want to find the average energy, we need to multiply energy for each state, which is En, we find out here, times Planck distribution of these particles, yeah? And this is what we've done. So it's En times a Planck distribution for each of the energy. And also to make your life even more complicated, in case if you are not, you started follow me before, we need to multiply by 2, because for photons we have 2 independent polarization. So what we can do over summation over nx and y and nz, yeah. And in this case, it will be let's do it. Sorry, guys, I'm just trying to think how to cut some steps. So let's go back to here. So 3D box energy, we write it down as summation of nx and y and nz, or we can write it down as just hc over 2l times n, where n is equal summation of all of it. So if we look in it as before, in the space of all possible states, so we can have it here nx, y, and all here positions, and or we can represent it as an n, yeah, in like spherical coordinates. I could see that you completely lost. I don't know. So what should I do? Let me just quickly give you the highlights of it, or otherwise I won't be able to explain you everything at all. How you like it? Because I want to give you some of information to derive from you how they get this spectrum graphs and all these Stephan's laws which you use for black body radiation. Oh, you completely couldn't hear, you didn't follow me at all.
Sucks being the only person on camera.
Okay. Okay, I could see that maybe some highlights.
Yeah, you're just kind of cutting off a little bit, or very often. The internet connection sucks. It's not your fault. It's either AT&T or Spectrum, whoever you have.
Okay. You know what, guys, let me do that. I will right now reset the whole internet in my house, so I will be back in like 2 minutes, okay? Because that does not work for us. It's dropping off, and in this case, I will just overgo quickly what we did before, and I will just go the main points only, okay? So, guys, I'm resetting the internet, and right now my husband will reset it out, and so you'll see me right now dropping the internet, and then please connect.
Okay, we'll do. All right, logging out.
Hello, everyone. Could you see me? Is it connection better, or it's still very bad?
It does seem better right now.
Yeah, it seems a little better.
Oh, okay, let's try. I know we waste half an hour today on all of these issues. Let's me see what we can do. So I hope I have everyone here. So let me make sure that I have my notes back. Hopefully you'll be able to see it. And I will try to highlight. Is it better connection here for my piece of paper?
So far, so good.
It's a little bit blurry, but
So far, so good.
it's okay.
Okay. I don't know what's I'm glad that it's not review, guys, because this lecture we can cut it out and I'm not as much worried. And next Wednesday lecture, I'm also less worried. For me, the most important that next Monday we'll have a good internet for everyone, okay? Because everything what I'm giving today next time is just extra information for you. Okay, I will go again over main topics which I wrote before. So we discuss photons properties. We discussed that it's bosons. It's a Bose-Einstein distribution. We discuss that it can create and destroy any quantities, and we come up with a formulation that chemical potential of photons is equal to 0. Does this make sense? Why chemical potential equal to 0? Guys? Once again, connection fully drops out. Hello?
Yeah, we can hear you.
Yeah, we can hear.
We can see yours, but the paper one is where it's a little.
Well, unless you're not moving the paper. Like if you're not moving the paper, then yeah.
I don't know what's going on. Sorry, guys. I don't know what's going on.
We can hear you though, so as long as you just like you keep going, I think we can hear you for the most part.
Yeah, but I want to use a piece of paper, and that's very disturbing. Okay.
I heard some professors don't even use paper boards or anything like that and just talk.
Sorry?
I've heard that some professors don't even have paper or a board or anything like that. They just lecture.
Are you telling me to change?
I don't recommend you go that route. Yeah.
Okay. It's very. It was supposed to be short, fun lecture, and this horrible internet completely ruined my favorite lecture about black body radiation. I'm so frustrated. Okay, guys. Did you understand why chemical potential equal to 0 and why we're going to go to photon, why photon-based Planck distribution, guys? Did you understand that part?
Yeah, we got the bits and pieces of it.
So I just want to go over main things. I will cut out some of the corners, but I want to make sure that at least we'll go fundamentally ideas. So photons is boson, so it's full of Bose-Einstein distribution. You understand that, yes?
Yeah.
Okay. You understand that why photons can be created and destroyed in any quantities. Do you understand this concept?
Yes.
Because look at it, if electron jump from one level to another, yeah, it's in this case it's release energy. And it depends what kind of jump from one energy to another energy, it will be different photon wavelengths, yeah? So it could produce different types of photons with different type of energy, and it will just produce it, or if you electron want to jump to higher level, it will absorb photons. So photons could be created and destroyed. Do you understand that part of the concept?
Yeah.
Yes. Yes.
Okay. So, such as photon could be created and the chemical potential should be conserved, it implies that chemical potential for photons must be 0. Is this concept clear?
Yes.
Yes.
Okay. So we'll go over like some of the main ones, okay? That implies that Bose-Einstein distribution could become a Planck distribution because we don't have a mu. Is that clear?
Yes.
Because mu is equal 0, we get this one. Okay, so up to here we're clear. Okay, now we can rederive this one. We can just different way how you can derive it, but let's ignore that. Energy of photons. What is the energy of the photons? It's a Planck constant times the frequency of photons. That's definition of the energy of photon, yeah? So we plug in, and this is what we get here. Instead of E, we get here HF. Are you with me with this formula?
Yeah.
Okay, so that's Planck distribution. So photon follow this distribution. Okay. Here we done that. Let's move back to where we were in this page, and then from that I will start to cut out some corners. So we use idea that particle in a box, and from that we can find what is the energy of possible energies. Yes, if there is particle in a box, its wavelength is quantized. Yeah. Does this make sense, guys? Are you familiar with the concept that if particle in a box, it has a quantized state?
Yeah.
Yes, because the wavelengths, if you can know the wavelengths, there's only a certain amount, that is particular wavelengths which could exist, yeah? So if you can like a string, you can have a string which goes like that, or it could be like two loops in a box, or 3 loops, or 4 loops, so it's quantized. In this case, if we know wavelengths, we can write a frequency. There is a relationship between them. In this case, energy is quantized. And that's all you see. It's in quantum physics. It's quantized. Photon's energy is quantized. From that, we can find what is quantized energy in 3D box. And that's it. Okay. So up to here, are you understand me up to this point? And I know the image become blurry again.
Yeah, totally.
Okay, so let me not derive it. So we can, I wrote it down that you can just find the energy as a summation of all possible states in a box, and you multiply energy of the states times the Planck constant for each of the state of the energy, and you need to pi times 2 independent of polarization. Then I will skip a step, which switch to spherical coordinates to do calculation of these states instead of like in Cartesian coordinates and spherical coordinates. And we can find out that energy of a particle in the box, the total energy per volume, and I'm writing only the answer, energy per unit volume, is equal to U over V is equal to integral from 0 to infinity 8 pi energy cubed over HC energy cubed 1 over E in the power of energy over KT minus 1 dE. Okay. That's total energy per unit volume. Could you see this formula, or you could not write it down due to the internet?
I can kind of see it, but yeah.
So that's what we got here. So we can talk about energy spectrum or Planck spectrum, where we talk about it, this value here as UE. So that will be, oh, that one doesn't write. So that we call it energy density or Planck spectrum. This will be the energy density. Okay, or it's called Planck spectrum. Okay. Okay, so it's energy density of Planck spectrum. This thing inside of the integral, that's called energy density per unit photon energy, yeah, or it's called Planck spectrum. So let's see how we can plot this Planck spectrum, and that's famous graphs which you always see for radiation. Okay, so I'm just trying to choose, guys, for you the most important concept, because I understand we don't have much time. Okay, sorry, I'll keep it like that. So we'll talk about Planck's spectrums. Okay. So Planck spectrum, so that's the one which we wrote it down. I'll rewrite it again. So Planck spectrum for photon, okay, it's equal to, again, internet drops. Could you see me, guys, or you couldn't see it again?
See you.
Yes, we can see.
Okay, I'm glad. Okay, so we will rewrite it slightly differently. We'll use it for simplicity. We'll call x is equal E over KT. And in this case, we can write our formula in the top as U over V equal to 8 pi KT in the power of 4 over HC cube. And here integral from 0 to infinity of x cube over EX minus 1 dx. Okay. So we rewrite that. And if we'll try to plot the spectrum radiation, the things which is inside of this graph, this one part here, spectrum radiation, as a function of x, yeah. In this case, you will see this graph which you saw before, where for low energy, it's look like that, or for low temperature. And as your, sorry, that's very high temperature. As the temperature decrease, it goes like this, yeah? So that's 300 Kelvin, 3000 Kelvin, this is 4000 Kelvin, and this is 5000 Kelvin. Okay, that's how the spectrum look like. So when you're looking at the radiation from the body, this is how the spectrum radiation looks like. This is the graph which you saw before. And when you look at this formula, you can see that it depends on the temperature. And here there is a, if you, especially probably in astrophysics, you saw this before, there is a Wien's law, which states that higher temperature tends to give higher photon energy. The higher temperature tends to give higher photon energy. Okay. Could you see it, or you completely couldn't see it?
I can see it.
Okay. Sorry, I will ask you every time because I could see the connection back. I just want to make sure at least I'm right now giving you only the main information. Okay. I want to also mention, because sometimes you want to find out what is the peak, yeah? So the spectrum peak is equal to, when x is, which is equal E over KT, is equal to 2.82. Okay. So if you can see that increase the temperature, if you not put it against the x, but if it will be against the temperature, you can see that peak will shift. And this is what you saw probably in the graph when you just plotted it for different temperatures. You can see that peak will depends on temperature. Yeah. Does this make sense? So we first of all peak increased and also the peak slightly shifted. Okay. This integral can be evaluated. So if we evaluate this integral, evaluate integral of from 0 to infinity of x in the power 3 e in the power x minus 1 dx, we can evaluate and find out that it's equal pi in the power of 4 divided by 15. In this case, we can find total energy density, and that's a different case. We're talking about, so here we're talking about density distribution, how it depends, like overall how it's distributed. But here we want to find what is the total energy. Does it make sense that it's two different questions? One of them to look how the energy distributes, what is the spectrum, and another one, what it's what it is total for the particular box, yeah, for the particular system. So the total energy density, total energy is equal to, just a second, just to make sure that total energy, put the total energy, in this case, U is equal to AT in the power 4. So it depends on the temperature in the power of 4, where A is equal to 8 pi in the power of 5, K in the power of 4, value divided by 15 HC cube. So it's a total energy of electromagnetic energy inside the box, yeah. Okay. How are you doing so far? So good?
I'm looking at that section where you wrote the integral to evaluate. I'm a little confused. Is that supposed to be t to the power of 4, or is that pi to the power?
Pi in the power of 4 divided by 15.
Okay, pi
That's
to the
the
power.
value of it. So if we plug in here, this value here, we can see that our energy depends on the temperature in the power of 4. Here we have T in the power of 4. We write it down, and everything else will be a constant. Okay? It's my paper just slightly too big to write it down for you to see both. Could you see it everything now?
A little.
Okay. So now just one more small note here, and then let's talk about radiation from hot body, okay, or hot object. So such as we find the energy, if somebody asks us to find the heat capacity or entropy, we also can do it, and that's not a problem. I will quickly write down. I hope the internet allow me. Well, let me keep it out here just for you, in case if you still need it. So entropy of photon gas okay, that could be found if we find the heat capacity which is equal to CV equal to partial derivative of energy respect to temperature when volume is fixed, and when we take a derivative of this one, that's easy, it's equal 4a T cube. And if you want to find absolute entropy for this photon gas, absolute entropy, in this case, at any particular temperature, what we need to do, we need to take the integral from 0 to T of heat capacity as a function of the temperature, but we put it like as a variable, another one, T prime, dt prime, okay? And if we evaluate this out, we will get that it's equal to 4/3 AT cubed. Okay. So that's it. That's about entropy. So you can see that this is what we can find out. And now let's move it to the next topic, radiation from the hot objects. Okay. Something which you may see before when we discussed it, what radiation of this model of black body radiation and so on, that we'll rederive it very briefly here. I'm skipping some of the steps, but I will show you main concept. How's the internet connection?
So far it's been
Better.
Okay. So hot objects emits photons, yeah? So what we will do for this model to find out how much objects emit, any object, like we as a human being, we have a temperature, we emit photons, we emit energy. How to calculate how much energy we emit? Okay, so to do that, for simplicity, we looked on a box and we'll have a small hole in this box and we'll find out how much energy is emitted from there. And from that, we can find what is emission for an object, okay? So what we'll do, we looked in a box. We have a box, okay? And we have a hole here with opening A. And it's look like the internet is better, is it? I think it's look like my internet's good again.
Yeah, for the most part, it's working.
Okay, good. So here we have a hole. So, and in this box, we have a photons, and these photons could emit in any direction, yeah? So what we will look out, we look how much photons emitted through this area. So what we look on this amount of photons which will reach this hole and will manage to escape there. And that's a standard model which they use. I will just go over this quickly because we have 15 minutes and I will quickly explain it. So we look, what is this? So we have a hole and you can see that how, like in this hole, how much photons manage to reach at any particular time. And that's a model we use. So that's thickness of this shell is CDT. It's because photons are moving with the speed of light, and then we calculated area here is equal to R dq. Assume this is angle. Sorry, theta. I'm sorry, theta, and it's like a 3D box here. This is the amount of it. And another one, it will be R sine theta. So if we look in a volume of escaped photons, we will get is RD theta, this small box of photons, times R sine theta d theta times c dt. Okay, that's equal to volume of this escape photons. And we find out of you before what is the energy density. So that's a volume, and the energy density for the any box of energy density of photons within this chunk. Okay, we find out before it was u over v, which we just derived before with difficulties. It's 8 over pi in the power of 5 divided by 15 kt in the power of 4 divided by hc in the power of 3. So now we know the density of these photons. We know this volume of number of photons, volume of escaped photons. So now we can find what is the whole energy. So we multiply this value times this energy, and then after that we'll need to integrate it. Yeah. So let's do it step by step. So in this case, energy of the chunk, it will be this one times this one. So it will be u over v times c dt r square sine theta d theta d phi. Are you with me, guys? Are you following me?
Yes.
And here one more thing is which we need to take account. So we calculated how much energy and how many photons we have in this particular small box. But will all these photons which locating in this small area escape through this hole? The answer is no, because these photons may point in all directions. Yeah, they like you're locating in this position here, but they could point not toward the hole, they could point in any direction. So we need to find out what kind of portion of these photons locating in this small square will point toward the direction of the hole, so they could escape. Okay, so most photons point in the wrong direction. And in this case, do not escape. So let's find probability of escape. And to do that, we need to find, so our object could point in all directions, but we need to look what is area is facing the hole, and in this case, they will be able to escape. And the probability of this is the area of the photon's direction which facing the hole, dividing it for all area is equal to 4 over pi r square. How is it? Is it clear how we get that one? We're almost there, guys. Is it? Did you clear how we get it, the probability of escape? Does that make sense?
Could you go over it? I'm a little confused on it.
Sorry? Could you repeat again?
Go over it?
I will keep the paper one. Yeah.
No. Could you go over it one
I
more
will
time?
go over that. Okay, sure. So photons could go in any direction. Yes. So
Sure.
let's make it in one dimension. I know that you're locating in your room, yeah, and you have a door which will exit you to run away. But you can randomly run in any direction in your house, yeah. Only particular angle in your directions of your random running will allow you to exit the door, yeah.
Yeah.
And that's exactly what we find out. So for us, we have a 3D shell, and 3D shell area is 4 pi r. And for us, area which will photons which will escape here to come to this from this area to here, yes, is equal a cosine theta, its area, and we'll need to take into account that it comes from the side, so it will be a times cosine theta. That's the area which they will see. It's a cosine theta. Okay, so if you're locating here, that's the area of escape. Okay.
Okay.
So if you're locating here, you have this radius, and only this area, a times cosine theta, allow you to escape out. Okay. In this case, we find what is the probability. We all possible directions, or we divided direction which allow us to exit to for all possible areas. In this case, we can find out what is the amount of energy that escape, the amount of energy that escape. In this case, from this chunk, is equal to a cosine theta over 4 pi r square times u over v times cd times r square sine theta d theta d phi, and we can see that r square could be cancelled. And then if you want to find the total energy, we just need to integrate from 0 to 2 pi d phi, from 0 to pi over 2 d theta of that here. Yeah, we integrate it out, and we get that if we'll do that integration, it's equal to a over 4 u over v c dt. Okay. And from that, there is a terminal we introduce as power emitted per unit area. Power emitted per unit area is equal to, if it's power, it means we divide it by time. If it's emitted per unit area, it means that we get rid of area, so it will be just c over 4 u over v. Okay. And if we plug in our values for u and v, which we find before, remember we find that u and v is equal to this one here, the total areas, yeah, u and v, we have from there we can find this variable. So we plug in these values here, we can find out that power per unit area is equal to sigma times temperature in the power of 4, and that's called Stephan's law. And he discovered it in 1879, and this Stefan-Boltzmann constant is equal to 2 pi in the power 5 k in the power 4 divided by 15 h cubed s square is equal to 5.67 times 10 in the power minus 8 watts per meter square Kelvin 4. Sorry. Okay. And that's Stefan laws, which you probably saw before. Questions? If not, we'll go for the last bit, just a few more lines. How are you doing, guys? So far, do you understand how we get to Stefan's law?
Yes.
Okay. So that's how we end up. That's why I want to write at least the main formulas that you understand how these formulas come up there, because you use it. I'm sure you saw this formula before. Did you see this formula before, guys? Maybe not, but you'll have also homework based on it. So let's talk about the last bit, black body radiation. Oh, this pen does not write down. Sorry. Semester is finishing and my pens are running out. Let's do the last section. Black body radiation. Okay. Black body radiation. So we talk about power per unit area. So if we want to find total power, how much energy is emitted, yeah? In this case, we need to multiply by area. So, and there is also, so power emitted is equal to this Stefan Boltzmann constant times area times temperature in the power 4. And if we have a situation when we have a not fully emissive subject object, but there is only fraction of a photon is absorbed, yeah. So in this case, the power formula looks slightly differently. It's equal to the same letters, but we also have emissivity. So we have this letter E here as well, which stands for emissivity, okay? And it's vary from 0 to 1, okay? It depends on the object, and that's the area, okay? So what is emissivity? Emissivity, oh, sorry, right. Emissivity of material, epsilon, is fraction of a photon absorbed. Fraction of photon absorbed. And you couldn't see it, I'm sorry. Fraction of photon absorbed. And if you have a black body, it's equal to 1. And if you have a reflector, it's equal to 0, yeah? For example, if your eyes in a snow, it's white colors and it's quite a good reflector, in this case, emissivity will be closer to 0. And if you something black body radiation, in this case, it's closer to 1, okay? So that's pretty much it. And you can see that let's look at this formula and analyze it. And it's the last bits which I want to discuss with you, because that's an important formula. For example, you want to find out, and I think maybe your question in the homework somewhere it is, you have it, how much energy you radiate. How to find it? You know what is your temperature of the body, yeah? You know, you can approximate what is your area of the skin. So you let's assume your black body, you have emissivity as 1. So you emit is everything. In this case, and then you want to find out over a certain time. Let's say if you will be out of clothes in the middle of winter, kicked out in the outside of the street, after how much energy you will lose after 5 minutes. In this case, you can calculate your temperature of the body, area of your body, and you can calculate what is the power, and to find the total energy, you need to multiply it by time. Okay. And also, you need to remember that black body, they radiate depends on the temperatures we discussed. It will be different wavelengths, and our body, what kind of wavelengths of radiation it emits, guys? Infrared, yeah. And so our body, like room temperature radiates infrared, yeah. And what kind of temperature need of the object to emit red colors, around which corresponds to around 1,000. Oh, sorry, I already wrote it down. Red colors, it implies that you need to have a temperature is around 1,000 kelvins. And if you want to emit something to the blue color of visible spectrum, you need to have objects with a temperature around 10,000 kelvins. Okay. So by looking what kind of radiation you have, what kind of wavelengths it radiates, you can find out what is the temperature of the radiation. Okay. That's pretty much it, what I want to talk to you about it. So that's, if you look in these graphs, which we discussed before, so if you look in the temperatures, this will shift with temperature. So it's 5,000 Kelvin, 4,000 Kelvin, 3,000 Kelvin, and you can see that that with the temperature, the wavelengths will shift. Okay. Sorry, again, I'm not showing you out, and nobody mentioning because I don't think that anyone listening. Okay, I'm done. I'm sorry, guys, it was quite a hectic. It's supposed to be one of my favorite lectures, but it's not enough to be as good as I was expecting.
Thank you, Professor.
Blame the internet.
Yeah. Do you want at least hear a couple jokes?
Jokes.
Sure.
Please.
At least I could tell you jokes. It's from my optics class. So if you'll be in my optics class, you'll hear them again. I'll choose the best one. A red, orange, and a yellow, and a green, and a blue, and indigo, and a violet phaeton walked into a bar. Bartender says, "Been rainy today. Looks like the sun is coming out."
Oh, rainbow.
Yes. Yes. An X-ray phaeton walked into a bar and the bartender says, "Can I get you something to drink?" The X-ray phaeton said, "No, I'm just having a look inside." Okay. What else? I will give you one more. I'm not sure if you will. That one is classic. A phaeton stopped at the bar and asked if there was a room to rent. The bartender said, "Sure thing. Can I take you back up to your room?" The phaeton said, "No, I'm traveling light."
Professor, where do you find these?
I don't know. It's just some of them I know from before. For photons, I just find some of them. Some of them comes from years of like hearing funny jokes, you know. I just feel like, especially right now with the COVID, you guys, I feel so sorry for you guys, you know. Okay, I will tell you, are you familiar with the fluorescence of the object? Have you done anything with fluorescence? If you never did fluorescence, you may not get at it, okay? I'll tell you, that's my favorite because I did fluorescence imaging, so it's one of my favorite ones. Okay, A green phaton walked into a bar. The bartender said, the bartender said, "You look fluorescent." The phaton turned back and left. Sorry, I missed the whole job. Could I start again? I'm sorry. The green phaton walked into a bar. The bartender said, "You look fluorescent." The phaton turned red and left. That idea is because the green light photons, when they hit the objects, they hit, for example, sands which fluoresce, and they fluoresce usually red, and they go back. So it's they hit and fluoresce in opposite direction. So they left the object and they change the wavelength from green to red. That's the whole idea. So it's my favorite if it is fluorescence. That's it. I'm done. I realize I'm recording. I will cut some of this recording. So
I say you leave the recording.
yeah, I just left now. Yeah, sorry. I keep it for jokes. I will cut it out. So you will have a homework problem based on radiations. Something simple where I think you need to do for the using this Stefan Boltzmann constant and calculation. Everything else, just derivation of that. We have one more lecture. Good luck, guys. I hope to see you on Wednesday. Please try to attend the colloquium. It's done specifically for you, this colloquium. Okay. Good luck.
I had a quick
Thank you,
question.
Professor.
Sure.
When do classes officially end? I mean, when do finals weeks start? I thought we had a lecture on Monday, but I guess I was wrong.
No, we have a lecture on Monday, which will be our review.
Oh, okay. Got it.
So we have one more topic, which will be this same hectic. I will cover just a little bit, very rushly, just give you bits of information regarding of Debye theory of solids. And I will quickly talk about Bose-Einstein condensator. Just quick overview, so at least you know a little bit what does it mean, okay? And that will not be in a test. That's just for you to learn, so you at least have some idea what it is. And on Friday or next Monday, we'll have a review.
Got it. Okay. Thank you.
And when's our final again?
Wednesday.
Next Wednesday.
5:30. Yeah, next Wednesday in 1.5 weeks.
Okay.
Almost there. I know. It's from one side it's good, from another side it's scary
Yeah.
for you.
Yeah.
For me, it's just good because it's will be over soon. For you, it's also scary. Yeah. Anything else, guys? You can always write me questions. I know nobody comes to the office hours, so I assume everything is clear and you know what to do, or you completely lost track and you don't care anymore.
Well, I have class during your office hours, so that's my excuse.
I see. Okay. Okay, guys. Have a good day.
Thanks again, Professor.
Thank you, Professor.
Bye.
Bye. Thank you.
Thank you, Professor.
Bye.